Hi everyone, I'm Pedro. I'm a PhD student at TU Wien, and today we're going to explore how we can use browser compliance tests for automatic vulnerability detection. This is joint work with Lorenzo Veronese, with whom I share first authorship, Valentino, Dalla, Valle, Stefano, Calzavara, Squarcina, and Pedro, Adão, and Matteo, Maffei. Let's start with a quick overview of the web platform. At the core are the specifications. These dictate how web platform components should work and help ensure that browsers and all devices that are part of the web platform are consistent with each other. However, the specifications are written informally in natural language, and they're managed by several entities such as the W3C, W2G, and the IETF. This introduces some ambiguity and some unintended interactions between web components, which can lead to security issues. Web browsers implement these specifications and are extremely complex pieces of software. Their sheer size and complexity means that security issues are inevitable. Also, how can we ensure that browser implementations are actually following the spec and doing so consistently with one another? For that, we have the web platform tests. WPT is a browser compliance testing framework and test suite, which is developed and maintained by both browser developers and specification writers. WPT is extremely comprehensive with around 200,000 subtests covering the vast majority of the web platform. However, it deals with compliance and not security, so we cannot really extract security guarantees from WPT test results. Whenever a new feature is added to the web platform, its specifications are manually reviewed by experts who try to find security issues. However, manual reviews are error-prone and are also not scalable, especially as the web platform grows and more interactions need to be considered. And us humans are just not equipped to deal with such level of complexity. Besides being error-prone, they're also slow. So manual reviews take significantly longer to find security issues than an automated approach, for example, would. And this is also what we argue for and the core of our research, how we can apply automated techniques, analysis techniques to mitigate these issues. First of all, we need a few ingredients, but the most important one, and as we've also heard in today's keynote, are a clear definition of the security properties we want to enforce. For the case of the web, these are web invariants. So web invariants are security properties of the web that are always expected to hold. As an example of a web invariant, we have the following property, which is describes the general case for the mixed content policy. It states that insecure resources fetched from secure pages should be blocked. The real invariant is a bit more tricky and involves a lot of specification jargon, but this is the main concept, the main idea. In previous work, we explored web invariants in conjunction with a formal browser model to find security issues and logical flaws in the specifications. This time around, we focus on finding security issues with the implementations themselves, so in browsers. Our approach starts by defining a set of web invariants. We focus on these two mechanisms, cookies and mixed content, since they have clear security implications and their specifications are relatively compact. Then we instrument the three most popular web browsers to collect relevant events that we then aggregate in execution traces that represent browser behavior. We then verify these traces against our invariants in the hopes to find invariant violations, which by design will have security implications. Now, this all may sound a bit trivial, but I assure you it's not. First of all, defining web invariants is an open problem. There are no clear algorithms or procedures to follow. It involves reading and understanding the specifications, which can be ambiguous, and when they are, we need to determine what is the expected behavior of a given web feature that we're looking at by the community. Then, regarding the instrumentation, collecting relevant and interesting events is tricky because they can occur at different levels within the browser. So a complete instrumentation must be multi-layered. So for example, if you want to track JavaScript API calls, we can do so through the DOM or at the engine level. But if we want to monitor internal browser structures like the cookie jar, we need other approaches such as using the extension API. And speaking of, these APIs are also not totally consistently implemented across browsers. For example, Chromium enforces manifest v3 for its extensions, while this is not the case yet for Firefox and Safari. Then, even if we manage to have the perfect instrumentation, we need to lead the browser to explore a wide range of behavior if we hope to find anything interesting. Manually writing tests, again, is not scalable, and other approaches such as fuzzing or differential testing usually focus on specific mechanisms, and we're trying to be as generic as possible. So how do we address these issues in our pipeline? We tackle the coverage problem by running our instrumented browsers on the entire WPT test suite, which is very extensive and lets us capture a wide range of browser behavior. Then our instrumentation consists of a cross-browser extension, which collects events in JSON. We then lift these events to execution traces in SMT. On the other hand, we encode our invariants as logical implications in first-order logic, and we then use an SMT solver to find violations into these invariants. Let's look a bit at the trace collection part of our pipeline. Our extension monitors three main components. So we monitor JavaScript API calls by injecting content scripts in every iframe. These content scripts then proxy certain JavaScript API calls that are configurable. For example, we can track accesses to document.cookie, calls to fetch, and more. We also track changes to the cookie jar through the cookies extension API. And we monitor the network activity through the web request extension API, so we can track network request responses, and this includes also redirections and so on. Since in manifest v3, some data became transparent to extensions, we also add an external proxy so that we can collect a bit more information and get a more complete overview of the network, and we then merge this information back in our traces in post-processing. So here we have an example of how our pipeline would produce an execution trace from a test. We have a test that's running on a secure page that's simply setting a cookie with name A and value B and the secure attribute. This should work since we are in a secure page. Then it asserts whether the cookie was actually set by getting all cookies from document.cookie and verifying that the intended cookie was returned. By running this test in our pipeline, we get an execution trace with three events. The first one, a JS set cookie event, which corresponds to the first assignment to document.cookie, and we can see that it's parameterized by the actual string that was assigned before to document.cookie. Then we obtain a cookie jar set event, which tells us that the cookie was actually set in the cookie jar. Otherwise, this event would not be in the trace. And here we can also gather information about how the browser parsed the assignment to document.cookie. So we get the value of every cookie attribute. In this case, secure is true. We get the domain, the path, the name, and so on. Then finally, we have a JavaScript get cookie event, which matches the call to document.cookie. And here we can see that the cookie was actually returned. So the cookie A with value B was actually returned in this execution of the test. Okay, we define 9 web invariants, 7 about cookies, and 2 about mixed content. And after executing our pipeline on the entire WPT test suite, we obtain violations to 5 of these invariants. In total, we obtained 101 violations, which we distilled in 10 unique vulnerabilities. We reported these vulnerabilities to the affected browser vendors in 8 individual reports, which were all acknowledged, and resulted in 2 CVEs, a complete mixed content policy bypass via framing on Safari, and a same-site cookie integrity violation on Firefox. This also led to discussions with specification writers and maintainers, which led to some changes to the RFC 6265 bis, which is the cookie spec. Out of the 101 invariant violations we obtained, 15 were false positives. These are mainly due to 3 root causes, being missing events. This happens when our instrumentation has low visibility on a given component, or through either browser features or browser bugs. It can also happen. Then another root cause was incorrectly ordered events. This can happen since there is some non-determinism in how JavaScript event listeners are scheduled, and we can have out-of-order events. Also, our timestamp granularity is not as fine as we would like, and we can also obtain some timestamp collisions, which we then need to disambiguate in post-processing, which can lead to false positives. And finally, some events in some browsers can have some missing information. For example, request objects that we obtain from the Web Requests API in Safari don't have the resource type parameter, and this is very useful and used in our invariants, so we cannot reason about those, which can also introduce false positives. So we use web features to analyze web features, and this is an inherent limitation of our approach, and it generalizes to software verification, software testing as a whole. However, since due to the number of false positives we obtained, we're very confident in the output and the correctness of our pipeline. So we propose a lightweight approach to invariant verification that can be easily integrated in today's browser compliance test pipelines. We show that in conjunction with web invariants and automated analysis, can detect invariant violations during development, so before they actually reach production. It does have some limitations, but these can be mostly or totally mitigated with better support for instrumentation and introspection mechanisms by browser vendors. And finally, all of this only makes sense if we actually have and agree on a set of web invariants that we want to verify and enforce, and we still don't have this as a community, and this should be a priority. There are a few things that we couldn't discuss in this talk, like, for example, how we encode the invariants, the attacks we actually got and reported. Please, it's all in the paper, please come talk to me. I'll be here until Friday, so feel free to reach out. I'll be happy to discuss it with you. And yeah, thanks for listening.